Okay, let's start the lecture. Couple of announcements. So people who are on a wait list, I think that you can join section B, which is an online section, I believe. So whoever is on the wait list, you can join the class. At least that's my understanding. There were a couple of questions about the projects. I noticed on Piazza. So the projects, as I mentioned before, could be done in the groups of 3, or you could do it by yourself. Right. So some people prefer to work by themselves. Generally, if you have groups of 3, you can accomplish more. So that's the reason why. Any other logistical questions before we start? Yes. Do we have GPU resources for projects? Yes, we're going to have some GPU resources. It's not going to be unlimited. But you will have access to, I believe we just got approval from Pittsburgh Supercomputing Center to get you some GPU resources. But again, the resources are quite limited, so you won't be able to like fire up thousands of GPUs and do so it's going to be fairly limited for the project. If you have access to your own GPUs, or if you have a computer with a GPU, that will help a lot as well. At the same time, yes, you will have some access to GPUs. And for the second homework assignment, you will have to be, the homework is going to be set up in a way that will require you to use GPUs. So you will basically, at that time, we'll make it happen. Yes?
Are we going to use TensorFlow to deal with GPU issues? Or?
Yeah, you can use whatever software you want. Generally, the preference would be to use TensorFlow. Some people prefer to use PyTorch. It doesn't really matter to us what you use or what framework you're using. This Friday, there is going to be a recitation, I believe, at this location at 1:30. And it's going to be about open AI gym environment, which is where some of the homeworks that you're going to be doing is going to be based on. And it's a very easy environment to use. And there's going to also be sort of a little tutorial about TensorFlow, right? How to set it up and so forth. But again, the choice of the package that you want to use is up to you. Okay? Okay, so today we're going to talk about some strategies for actually learning optimal policies. And again, today's lecture is going to be a little bit more at the introductory scale. Next week, we're going to start jumping into Monte Carlo evaluation and then later on in TD learning and such. So we're going to jump into these questions in more detail. But today, hopefully, you'll have some basic idea of how can we start searching for optimal policies. Also, the slides are online. And the reading material is online. So please make sure to, do the reading. Because if you don't do the reading, and you're going to be lost doing assignments. So it's the book that's provided. It's free online. So make use of this resource. And it's an excellent book if you really want to learn about reinforcement learning and deep reinforcement learning. Okay, so just as a reminder, what is an MDP? As a reminder, we have S, which is a finite set of states. So for now, we're going to be making assumption that we have a finite set of states. A is a finite set of actions. Think of it as finite discrete set of actions we're operating with. T is a state transition probability function, right? So given an action, or given a state and the action you're taking, the transition probability actually gives you the distribution of possible states, next states, right, at the next time step. R is the reward function, which is the expected reward, given that you're in a particular state and taking action A. In many cases, as I mentioned before, for a lot of problems, the reward function is going to be deterministic. So if you take a particular action, you get the reward, which is 10, or you get the reward, which is -1. In more general problems, you might actually have the distribution of possible rewards, right? Sometimes in exactly the same state, if you take the action, you might get 10. Sometimes you might get 5. Sometimes you might get -2, right? So this is a little bit more complex systems. For the purposes of this course, we're mostly going to be working with the settings where this reward function is going to be deterministic, right? So there's only one value. But in a more general setting, it's the expected reward given the state and the action. And y is the discount factor, and we're going to be making assumption that y is lying between 0 and 1, right? So prediction, let's remember what the prediction is. Given an MDP and a policy, so somebody gives us the policy, find the state and action value functions, right? So this is the problem of trying to figure out what the value of the states or what's the value of state action function, right? The Q function. Once we have the policy. Once we have the policy, we can compute that. Optimal control, given an MDP, find the optimal policy, right? Sometimes it's also known as a planning problem. So once you know, and again, what's known, I think somebody asked me last time, what is known in MDP? Well, what is known to us is the finite set of states. So we know how many states we have, what they are. We know the set of actions we need to perform. We know the state transition probability, right? And we know the reward function, as well as the discount factor. So this gives us a complete definition of the MDP, and this is something that's given to us. So find the optimal policy, right? And in general, you compare it with a learning problem with missing information about rewards and dynamics. So what happens if we don't know what the reward functions are? What happens if we don't know what the dynamics of the environment is? That becomes a much tougher problem to deal with. But we're still going to be considering finite MDPs. So for now, we're going to be considering finite states, finite actions with known dynamics. Okay? So we're going to make assumption that the transition function is given to us. Now, obviously, this is finite sets, state space, and finite discrete set of actions is not always realistic, right? In many cases, your actions would be continuous, or your state might actually be, if you think about a robot navigating in the world, and the input to the robot is the camera input, it's very difficult to say what is the finite set of states. It's like a combination of pixels, an infinite state, right? So we'll deal with that later. So we're going to look at 4 things. We're going to look at the policy evaluation. Just a reminder, given the policy, how do we evaluate? How do we compute the values in the Q functions? Then we're going to look at ways of optimizing for the policies. And there are 2 real approaches. They're very related to each other, but there is something that's called policy iteration, and then there's something that's called value iteration. So if you look at a lot of literature, if you look at the papers, sometimes people say, like, this is my value iteration algorithm, and I'm finding the optimal value function, or this is my policy iteration. I'm trying to find the actual optimal policy. Obviously, if you have the optimal value functions, you can recover policy, right? Or if you have the optimal policy, you can recover the optimal values of the states, right? So everything is connected to each other, depending on how you set the problem up. And we're also going to look at the synchronous dynamic programming as a way of computing these things. Okay? So let's remind ourselves what's a policy evaluation. For a given policy pi, we compute the state value function. Right? So we're going to be using the notation v sub pi, which basically means we're computing the value of the state given a policy pi. And the definition of the value of the state is just the expected cumulative discounted reward, starting at a particular state S. Right? So we start at the state, and if we could compute the expected discounted reward all the way into the future, that would be the value of the state. Okay? Now, remember that v sub s, the value function, is implicitly given by the Bellman equation. And again, we'll come back to this equation over and over again throughout this course. That's the recurrence relation that we've defined last time in our class, right? The value of the state is expectation over the policy of the reward plus the discounted, and this is essentially the expected value of the next state. Oh, sorry, it's kind of like you're marginalizing. You can think of it as marginalizing of all possible future states where you're transitioning to, right? So remember last time when we talked about the value of the state, we've talked about the value of the state being decomposed into 2 parts. The first part is the reward that you get by taking action. In this case, you can think of it as an expected reward where expectation is taken with respect to your policy, right? So if you have 2 actions, each with probability 0.5, then your expected reward is basically, if you take this action, what kind of reward would you get? If you take this other action, what kind of reward would you get? Weighted by the probability of choosing that action, right? And remember, last time we've talked about these two pieces. There is a reward piece, and then there is the value of the state piece, right? So how good, on average, if you take an action, you get the reward, but how good, on average, the state will be when you transition to that state, right? And in this case, these are just the definitions, and that comes out from the Bellman equation. So think of it as a system of simultaneous equations. In the settings where S is discrete or finite, then that's the set of basically linear equations, right? And everything is specified. Pi is given to us, R is given to us, the transition is given to us, and we're just going to be solving for these ones. Okay? Just a little bit, we can rewrite this a little bit, sometimes called Markov reward process. We can basically say, well, you can push the expectation inside, right? The summation of some of the policies. So we can say, well, this is the expected reward, as I was mentioning. We're going to be denoting it as RS pi, right? And this thing here is, again, it's kind of looks at the value of the overall state by marginalizing over possible future states and over all possible actions, right? So here you are basically saying, if I'm a particular state, if I take over all possible actions and all possible future states, what would the value of the future states would be according to your value function? That's on average is telling you how good the state is. Okay? And we're going to be denoting this as this quantity here, which you can think of the expectation, and then this is the expectation with respect to the transition metrics of the value of your policy. Okay? So why do we need to basically write it this way? Well, it's just for convenience, right? And again, here you can clearly see what is happening here. This is a matrix. This is a vector. This is a vector of size, the cardinality of the state space. And so you can basically think of it as a set of linear equations. So for MDPs, again, we can this is just an illustration. And if you look at Sutton and Barter's book, they're basically using a lot of notation of this sort, just basically telling you what the relationship is, right? From state to S prime. And that's the relationship. Okay? Now, the Bellman expectation equation can be written concisely using the induced form, right? And that's the reason why we're making it, just simplifying a little bit of a notation. And as you can see, this is just a set of linear equations, right, in a discrete space. And so we can basically find the solution, right? Because T sub pi is a matrix, V is a vector, and R is a vector. So now we can just basically compute this quantity, invert it, multiply it by R, and we get the value function, right? So it's a direct solution of complexity n cubed. Okay? So what does that mean? That means that if I give you the policy pi, I can compute what T is, I can compute what R is, these are expectations with respect to the policy, and I can solve for the optimal value of this, for the optimal value function, given that specific policy. So this is just a simple, basically solving a set of linear equations. Yes? The summation is, you mean how this thing is disappearing? Yeah, you're basically folding this in. You can represent this thing as, as a matrix times vector multiplication. Yeah. This is just a simplified notation to essentially just write a sequence of linear equations and, finding the optimal value function for order n cubed. Now, obviously the issue doing it this way is n cubed. Yes?
Is the matrix always invertible?
Yeah, so you have to like put some conditions on the transition operator to make sure that it's kosher. It might not be invertible. In many cases, you would regularize it and such to make sure that it is invertible, right? Just like the set of linear equations, like is this a solution or not, right? So there are some conditions on the transition dynamics that you have to put to make sure that it's solvable. But the point that I want to make here is that it's of complexity n cubed, right? So generally speaking, it's very difficult. Like, if you go beyond 5,000 states, 10,000 states, it's very hard to solve it, right? And in practice, we'll see longer term that we're going to be working with very large state spaces. Okay? Okay, so we can also use iterative methods, right? And just like, you probably have some knowledge of linear algebra. Like as soon as you write this down as a set of linear equations, then things become easier, right? You can use some iterative methods to solve a set of linear equations. It's essentially what's happening here, right? Given expected value function at iteration k, we back up the expected value function at iteration k plus 1. So we can basically say vk plus 1 has to satisfy this expression, right? So given v sub k, we can compute v sub k plus 1. And we can just iterate. Right? Given vk sub plus 1, we can compute vk plus 2. Right? So it's just an iterative method. And again, here everything is known, and notice that pi is given to us, so we know what the policy is, right? So at the high level, it really is just you solving a set of linear equations. That's all you're doing. Right? So if you look at these equations, it might be a little bit scary, like these are sums and stuff like that, expectations, really is a set of linear equations. So a sweep consists of applying the backup operator v to v prime for all the states. Right? Obviously, if you go here, you have to apply it to every single state. Okay? And so you're basically applying the back operation iteratively. So going from v0 to v1 all the way up until you basically converge. Okay? Let's look at the example. And we'll come back to this example again. So let's say that it's a fairly simple standard example, a small grid world. You have an undiscounted episodic task. So there is discounting factor gamma is 1. Anytime you make a transition, your reward is -1 up until you reach the terminal state. Right? So you have non-terminal states pretty much everywhere here. And the terminal states are these two states. So once you reach that state, you stop. The episode stops. So actions would take the agents off the actions that would take the agent off the grid basically leave the state unchanged. So if your agent is here and the agent wants to go here, it just basically stays where it is. Okay? And the reward is -1 until the terminal state is reached. So obviously you can kind of think about what the optimal policy here would be. What the optimal policy here would be? Well, the optimal policy here would be just go here and here. Right? You can basically, that would be the optimal policy. Or if you think about over here, well, let's think about like over here. The optimal policy would be 1, 2, 3, or it could be 1, 2, 3. Right? So there are two actions that you could take at that location. Now let's look at the policy pi, which is just basically a random policy. So at any point in time, your policy is just take a random action. And now you want to compute the value of the states for given that policy. Let's say it's a random policy, the value of the state for each one of those grid worlds, right? And this is what the value of the states would look like. And so you go on and you go on, and then you basically at infinity you're converging, right? And you basically can see that, so here the value of the state is -14, here it's -18, here it's -20, right? So the reason why you're seeing that it's -20 here is because it takes much longer, to go to that state compared to this is -18 because it takes much less to get to that state. But again, it's a random policy, right? So the value function here would be the optimal value function for this policy. Now let's look at this a little bit, just as an intuition. If I give you this value of the state, okay? If I'm at this location here, and the value of the state is -14, right? Or let's even better. Let's say I'm over here. Sorry, for some of you who can't see, is like minus 20 here. If I'm in this state, and I have my value functions right now, how would I change my policy? Because my policy is random right now. Can I change my policy that would do better? Of course. You look at this, you basically say, well, if I take this thing, it gets me to minus 22. If I take this thing, it gets me to minus 20. If I take this thing, it gets me to minus 14. So maybe I should change my policy, given my values of the states. I could change my policy in such a way that I can improve my policy. So obviously you would move here. So that's why this is sort of creates an iterative algorithm intuitively, right? Where you compute for given policy, you compute the values, and then there is a second stage, which is greedily figuring out, is there a better policy? I guess there was a question?
Yeah, so would you go left or would you go in all directions with another distribution that's skewed toward the left?
Yeah, we'll come back to that. We'll come back to that. In many cases, you would go in distribution proportional to the Qs, right? But what I'm trying to basically make a point here is one very important point. You start with a random policy, right? You compute the value functions. Given the value functions, you now have the information to update your policy to be a better policy, so that your next policy is a better policy, right? And you can see it from here. Clearly, this information tells you something about, like, being in this state is really bad, even for the random policy. You don't want to be here. You basically want to be somewhere here or here, right? And if you're here, there is no reason for you to go here. Or at least the probability of going here should be much higher than the probability of going here, right? That's the essence of kind of iterative procedure for optimizing your policy in sort of this tabular form. Let me just give you a little bit of math behind, and again, you should look at the book for proving that iterative policy evaluation actually converges, right? And the idea is simple. There's a typo here. So in operator F, on a norm vector space X is a Y contraction, provided that for all X you have this inequality. It should be F, it shouldn't be T. It should be F. So the contraction mapping is basically saying for a gamma contraction F in a complete norm vector space, F converges to a unique fixed point in X at a linear convergence rate of gamma. Okay? These are basic results from linear algebra. And this is basically a simple proof that shows that you're not going to kind of run off and not converge when you're doing policy evaluation. So consider the vector space V over the value functions. There are S dimensions, cardinality S dimensions. So think of it as on the order of thousands, let's say. Each point in this space is fully specifies a value function V sub S, right? And Bellman backup brings the value function closer to this, is in this space. And we can prove that, and therefore the backup must converge to a unique solution. So, so in these kinds of settings, you can actually prove that you can converge to the unique solution. And the proof sort of goes along something like this. A fairly trivial proof. We'll measure the distance between state value functions U and V by the infinity norm. And remember, the infinity norm is the largest difference between the state values, right? So if you have two vectors, you just basically pick the maximum of the difference between the two. So that will be the infinity norm. And then you have the Bellman expectation backup operator, right? Something that we've written before. And then basically what you can show is that this difference, if you apply this operator, you can rewrite it down. So here you're basically saying, well, it's the same thing as just writing them up. Then if you look at the definition of an infinity norm operator, you can write it this way. It's always lower bounded by this expression here. You just kind of like pushing the infinity norm inside, just by definition of the infinity norm and the definition of the maximum. Right? When you have two numbers, when you're multiplying a bunch of numbers, you take the maximum of this one, the maximum of this one, you're multiplying them, it's always going to be larger than what you have here. And then this is also low bounded by this quantity here, and the reason why, because T mapping It's a probability, so it's always less than 1, right? All the elements in T are less than 1. So now you basically have this construction, right? So every time you're applying the F operator, this form, you're basically going to be contracting. And so you're going to converge to the unique optimum, right? You know, you probably, like, for those of you who are really interested in the theoretical part, you should look at the book and then, you know, explain in a little bit more details. The point I want to make here is because of gamma here, being a number between 0 and 1, you're basically guaranteeing that you're going to be converging. So you're not going to be kind of you know, not converge. So the Bellman expectation operation has a unique fixed point. And by contraction mapping theorem, and then iterative policy evaluation convergence for that value, right? So now we've established one thing. Given the policy, I can come up with an optimal, or I can converge to the fixed point value function. Okay? Okay. Now, how do we improve our policy? Right? I gave you a little bit of a hint to sort of say, looking at the value functions, you can find out, you know, maybe there's a better policy. And it's, suppose we have computed the value function for a given policy. And let's say that policy is a random policy. So it's a really bad one. Or maybe even for some deterministic policy pi. Right? It doesn't have to be stochastic. For a given state S, would it be better to do an action A, which doesn't, you know, come from pi? So this whole thing generalizes to stochastic policies, but let's just make an assumption here because it's easy to visualize where policy pi is deterministic. So for a given state, policy produces you one action. So it's better to switch to an action A for state S if and only if the Q function of being in a state S and going to taking action A is bigger than the value of that state. Right? And we can compute the action state function from the value function by just looking at this expression. The definition of the Q function is, again, something that we looked at last class, and you can just compute this. Right? So what is this telling us? This is essentially telling us that you should change your policy pi and take the action, a new action, in the settings where the Q function is bigger than your current value of the state. Right? And that's exactly what we've seen last time. You basically have the probability of going to the state that's better. You basically go to that state. You don't go to the state that's worse. Does that make sense to you? Yes?
So the values are computed based on previous policy?
That's right. Yeah. The value functions are always, so given a policy, you compute the value function. You can always do that. Right? If you know the dynamics, if you know transitions, you know the rewards, compute the value function. Then, for given value function, you compute the Q function, because you only recover Q function, which is essentially telling you if you're in state S and you take this action, how good is it? Right? And then you're basically going to be choosing the action where this holds. Right? So here's and we're going to be doing this for all the states to get a new policy pi that is greedy with respect to v sub pi. So for example, here we can say take the action A for which Q function gives you the best value. Right? This is going to be deterministic policy, again, but we can do that. And that's just the definition of what the argmax is. Right? Over A of this quantity and argmax over A of this quantity. Right? So you, in this case, if you have deterministic policy, you compute the value of the states, and then you're basically greedily choosing a better policy, right? And what if the policy is unchanged by this? So it doesn't change. So whatever your previous policy is, you have the best actions. Then you basically have reached the optimal policy. Very simple algorithm. Okay. Now, throughout the rest of the course, so this kind of algorithms, you can think of it as, you know, working in a tabular worlds, right? Where you have state, which is discrete, you have actions that are discrete, and you're assuming that the state is very, not that big, and so now you can kind of find greedily the policy. The challenges then come along the lines of, well, what if your state space is large or even exponential? What happens if your actions are continuous, not discrete? This whole thing becomes much more complex in that setting, right? So in a very small grid-like worlds, you can do that. And you can prove all kinds of stuff. So the policy iteration, the idea of policy iteration is really comes from the fact that you start with some policy, maybe even random policy. You do policy evaluation to compute the values of the states. And then you do policy improvement. You gridify the policy, right? And that's exactly how a lot of kind of algorithms are roughly functioning. Like if you look at AlphaGo algorithm for playing Go, they sort of follow similar kind of style. Initially, your policy is random. You can sort of like take random actions. Then you try to estimate the value of the state by simulating the game forward and seeing like, did you win or did you lose? And based on that, you compute the value of the state, and then based on the value of the state, you again refine your policy, right? So that's roughly what's happening. Obviously, how do you deal with large state spaces and all that stuff is we'll look at it in this class. So here's the policy iteration algorithm. Sometimes it's very good to look at the algorithms. One thing I like about the book, the Sutton and Barrow's book, is that they have a whole bunch of different algorithms. So when you look at the algorithms, it's like the implementation. You can actually implement it yourself. So let's look at it a little bit more carefully. So let's say that v sub s, we just initialize it to some values. Could be 0, could be some random values. And pi, the policy, is going to be initialized some randomly for all the states. Let's make an assumption that pi here is deterministic. Right? So if some state, you randomly pick the action, or you pick one action. So policy evaluation. So you repeat delta set to 0 for each state. You basically compute the value of the state. This is one iteration, right? So it's a one linear update. And then you're basically saying, well, have I changed? Is my value changed by some delta? Or by some, in this case, small positive number, whatever the threshold is. If it's not changing that much, that means that I'm done. I've converged. Okay? This is just this update. And then the policy improvement essentially does the following. For each state, you take the current action, right, according to your current policy. Then you compute the maximum, the argmax. So you compute the action that's maximum over this quantity here, which is again the reward, and the second piece, which is the value of the state averaged over all transitions. And if a doesn't equal to pi, if your action has changed, then the policy stable is false, and you repeat. Okay? If the policy is stable, then stop and return v and pi, else go to step 2, right? So basically that means that the policy is changing. If the policy is changing, that means that you still have some room for improvement. So you go back to 2. You're changing your policy, you again do evaluation. You're changing the policy, you do evaluation. Up until the point where you no longer can change your policy. And if you no longer can change your policy, that means that you've reached the optimal policy. Okay? So here's an example, the same example of what would happen if you are doing this greedy sort of improvement of the policy. Right? So this is kind of what we've seen. This is sort of, if you given the random policy, this is what you get. And now, if you kind of start figuring out what's going on, here's like after one iteration, you see the optimal policy will basically say go here. Precisely because here you have minus 14. So all the other states are minus 20, minus 20, minus 18. And this is minus 14. So from here, you basically want to move here, right? So that's exactly what's happening over here. And as you see, once you do this multiple times, you're effectively reaching the optimal policy here, right? Now, in these cases where you have two choices, you can pick one, and it's still going to be deterministic policy. Okay? Yes?
Previous slide for the policy improvement part of the algorithm. So, what do you mean by is it A sample from the phi of S?
Right. So here we're making an assumption right now that our policy is deterministic. Okay, so we're just making the simplification right now that the policy is deterministic, which basically means for every state, the policy spits out one action and only one action. Now, you can generalize it to having a distribution of reactions, but the matching will basically have to be done a little more differently here. Okay. Now, one of the questions here that you might ask is, okay, when I'm doing this in practice, do I actually need to go all the way to evaluate my policy and then change it a little bit, and then go all the way to evaluate my policy and then change it a little bit, right? And it turns out you don't have to do this. And also for K, you know, I've already reached the optimal policy here, right, after just a couple of steps. So does the policy evaluation needs to converge to V? That's a question. Like, do you actually need the convergence? Or should we introduce some stopping criteria? For example, epsilon convergence of value function. Like, as long as you're epsilon close, then you stop. Or maybe simply stop after K iterations, right? So K3 was sufficient to achieve optimal policy. And generally, what you can do is you can update the policy after every iteration. So in other words, you can do intervening the two things. You can do policy evaluation, so you can improve your V a little bit, your value function. You can update your policy. And again, improve the V function a little bit, update your policy, right? And that's kind of gives you probably much faster convergence in practice. Yes, question?
In the last slide, were you really showing policy iteration? Because aren't you supposed to update the value based on...
Yeah, so generally, so this one is the policy evaluation for the random policy.
Okay.
Once you make a change here, for this new policy, you have to rerun this thing again to get a new values of the states. And then again, update the policy and run it again. Right? So every time you're changing the policy, your value function will change, right? Obviously, because you are executing a different policy, right? And so the question is, you don't really need to run up to infinity. In many cases, it will be sufficient for you to start with a previous value. So let me just come to this point, which is something that's known generalized policy iteration. So any interweaving of policy evaluation and policy improvement, independent of granularity, right? So you kind of going into the space of, given the policy, you do evaluation, maybe running a few steps. Given a few steps, you gridify your policy. You find, better actions. And then again, you do evaluation, you find the better actions. So it kind of goes into like, you update this and update the policy, you update the value, you update the policy, and so forth. So you don't have to run all the way up to convergence to actually get to the optimal policy. Okay? Any questions? Yes? Yeah, so it's a good question. In many cases, if you know something about the domain, you can initialize it differently, right? In many cases, when you don't know anything about the domain, it's hard to initialize it. So sometimes what actually happens in a lot of practical problems, and I think we're going to have a lecture on this, is people use something that's called imitation learning, which is to say, get people to do stuff. Like get a couple of grad students for this grade world and say like, what would you do if you start here? Obviously, any grad student, any person would just basically find the optimal path very quickly, right? So then you can take some of these samples and train your model to say, in this state, predict this action. If you're in this state, predict this action. So you can bootstrap your model a little bit so you don't start with completely random policy. So in places like whenever one good example is a game of Go, they basically collected a lot of people playing games of Go and just initialize the policy to say, if you're in this state, this is what the expert would do. So try to predict that move. If you're in this space, try to predict that move. So your policy is not completely random. Generally, when you're working with very large state spaces, random policy is just really, really bad. It's going to take you a long time, right? Because you imagine, you're doing completely random exploration, and then it's tough. Yes?
What are the trade-offs between stopping till we reach convergence and try to
Yeah, it's a good question. So can you show something about I think that in terms of convergence results, it doesn't matter. But in practice, what typically ends up happening is that you want to do only few evaluations because it takes time. So, if you're optimizing for your delta to say, I want the delta close to the optimal V value, in many cases, if you have two states, does it really matter whether you compute this to be 19.22 and this to be 16.24? You only care about that this is a better state than this, right? For the next policy to kick in, right? But at the same time, you have to be careful because if you have two states, and this one is the value of the state is 19.21 and this one is 19.22, then you need to really be granular, right? So a lot of it depends on, evaluation will depend on, how much difference you have in your states, because that can be a decision factor of what policy you're choosing. But generally, you don't have to go all the way to, doing policy evaluation. In practice, it just works better to do it this way. You do a few updates for evaluation, you update your policy. You do evaluation, update your policy, and so forth. Yes?
How do you make sure the policy converges to a one optimal policy?
I think there is a theorem somewhere that tells you that you can converge. Yeah. It's basically it's the same thing that we can show. I think we'll come back to this. We'll come back to your question. It's very similar. The proof is very similar as what we've seen for the policy evaluation, because with the policy evaluation, I can converge to the optimal. There's one optimal. Once I have the optimal, I can always improve the policy. I can't make it worse. I can improve the policy. From this one, I have the optimal one, and I can improve the policy. So by definition, it will have to converge, right? And under certain conditions, the policy itself is going to be unique. But it doesn't have to be. Like in this example where we've seen there are two actions that can lead to the optimal. So both of them are optimal. So, but you will converge. Maybe just one more question, and then we'll...
Is convergence guaranteed for a stochastic reward function?
Yes, I think so, because everything, when you think about the reward function here, it's an expected reward. So it will still be guaranteed. You just take expectations. Okay, so let me just make sure that we go over the slides, and maybe I'll take the questions at the end of the class. So the optimal policy can be subdivided into two subcomponents. The optimal first action, followed by the optimal policy from the next state. Okay, that's sort of a principle of optimality that we'll see. Kind of, it almost comes down from the Bellman equation. So the policy pi achieves the optimal value from state S, right? So if you're following a particular policy, it's equal to the optimal one, if and only if for any state S prime reachable from state S, pi achieves the optimal value from state S prime, right? So this is essentially saying that if I'm in a particular state, and if I take the optimal action, and then I act optimally after that, then I'm going to be reaching the optimal value of the state. Or that's why, in this case, I'm going to have the optimal policy. So it really comes down to this equation here. If we know the solution to the subproblem, so if we know the optimal values of the states, then the solution can be found by just one step look ahead, right? That's the definition. V star equals to this thing. So if I know V stars for each one of those S's, S primes, I can get V star of S. That sort of should be obvious. But now this comes to the notion of something that's called value iteration, right? Notice that here we don't really talk about policies. We're trying to find the optimal values. And the idea of the value iteration, which is kind of it's equivalent to policy iteration, but it's somewhat different, is to apply these updates iteratively, right? So you're iterating over these updates, and that's exactly what we've kind of we're solving initially, right? Given the policy pi, it's a system of linear equations. And the intuition here, you start with the final rewards and work backwards. So if whenever you have like big reward, that will influence what this thing is. And it typically works with loopy, stochastic MDPs, and so forth, right? And we'll come back to that. Here's the example of the shortest path, just doing value iteration, right? Just following this set of equations. And you can see that after 7 updates, you're basically finding the optimal value of the state, right? Once you have this optimal value of the state, you can recover policy from it. Because obviously, what's the policy here? Well, it's this thing, because you have smaller value, and then you reach the state. So for the value iteration, you want to find the optimal policy. And you basically, iterative application of Bellman optimality backup, right? You have the value 1, you update it to the value 2, and so forth. At each iteration k, for all states, you update vk plus 1 from vk. And eventually, you will converge to the optimal one, to the optimal value function. And this is again, instead of taking expectation with respect to your policy, you're always taking the maximum, right? And that's the difference. And notice that there is no policy that's showing up here. You just always greedily find the best action to take given your current values of the states. Yes?
So when do you use value iteration? When do you use class?
Depends. It depends. We'll basically, throughout this lecture, we'll look at both of them. Sometimes for certain problems, if you structure of the problem such that this might be easier, sometimes the structure of the problem, that policy iteration might be easier to do, right? Remember here, right now, we're working in a very simple environment. These are sort of called tabular environments, where things are discrete, your state space is discrete, your actions are discrete, they're not very large, so you're basically kind of doing everything by brute force, more or less. And so you're solving it this way. Complexity-wise, both are about the same. So it's not like one is more efficient than the other one. So here you define the Bellman optimality backup operator F star in the same way. If the operator is y contraction, if it makes the value function closer to at least y, and then basically you can have a similar proof saying that here, every time you update your value function, it's a contraction mapping, so you will reach the optimal point V star, the unique point V star here. Okay? Which is basically fairly straightforward linear algebra. If you look at Rich and Sutton's book, they go through that proof in a little bit more detail. So if you're curious about the definition of metric spaces and that kind of stuff and when it's possible, I think there's some extensions beyond metric spaces. So there's some generalization of these results. So the Bellman optimality operator has a unique fixed point. V star is a fixed point, and the value iteration will converge to V star. Okay? It will converge to the optimal one. And again, it should come as no surprise to you, right? Because if you know the rewards, you know the transition dynamics, how the world changes given the state and the action, what the next state is. Like, what that means is basically, if I'm here and I take an action, go right, I'm going to end up here. That's what transition dynamics is telling you. It's not like if I'm here, in more complicated environments, if I'm here and I say go right, then maybe with probability 0.8 I go right, but with probability 0.1 I'll go forward. Right? That's what this transition operator would model for you. And in particular, it's useful for modeling noise in the dynamics, because sometimes, you try to act, and with some probability, maybe your robot does something else. Right? So, just a little bit of diagram. You have a prediction problem. You use iterative policy evaluation. For the control, where you try to find the optimal policy, you can either use Bellman expectation equation plus greedy policy improvement, so it's a policy iteration algorithm, or you can use Bellman optimality equation and do value iteration, right? And so again, if you look at the papers on this topic, sometimes you see people are talking about value iteration, like value iteration networks, for example, is a recent paper that's optimizing for the value function in a specific way. Sometimes you see policy iteration algorithms that are trying to do that. So algorithm is based on the state value functions V. So complexity is in the order m times n squared, where n is the number of states. So it's better than direct evaluation, which is cubic, right? Because it's an iterative algorithm. So if it's order n squared, but again, it's of order n squared, and when n is large, it's just not scalable, right? Basically, whenever you work with a large-scale problem, anything that's beyond of order n, it's hard to solve. And you could also apply the exact same things to the action value functions, Q functions, right? And as we go through the course, we'll talk more about Q functions and Q networks and value functions and value iteration networks and so forth, right? I guess one hard thing for you guys to kind of think about is to really understand the difference between value versus the Q function and how they're relating to each other, right? Okay, now, to find the optimal policy is polynomial in a number of states, right? It's polynomial, which is good. It's not like an NP-hard problem. It's polynomial, but the number of states is often very large, right? And it's also going to be growing exponentially with the number of state variables. Curse of dimensionality, right? So if your state is not just one variable, but it's 10 variables, and each variable has many different values, then you basically have exponential growth, right? Because you have to consider all possible combinations of those variables. That's a standard kind of curse of dimensionality term. So in practice, classical DP can be applied, dynamic programming can be applied to the problems with a few millions of states. Okay, going beyond that is difficult. And again, when you think about millions of states, things, you say, well, that's a very large number of states. But if you think about, I have two variables. Each one takes, let's say, 100 values, and another variable takes 100 values. So that's your state of just two observables. 100 times 100 is already 10,000, right? Because you have to look at the combination. So if you have on the order of like 10, 20, 100 variables, you start looking at the cross product of all of them, then it becomes basically, you can't really do much about it. So all of the sort of these dynamic methods, dynamic programming methods, right? So dynamic programming methods is what we've seen so far. These are recursive methods. Basically, they require exhaustive sweep through the entire state set, right? We basically say, for all the states, do the sweep. If you have hundreds of millions of these states, how do you do that? So there are synchronous dynamic programmings that basically do not use sweeps, but they do the following. They pick a state at random and apply the corresponding update, corresponding backup update. So that's more like a stochastic version. You pick something at random, you update. Pick something at random, you update. And you're hoping that eventually you will converge. And that still requires a lot of computation, but it doesn't get locked into like very, very long sweeps. It guarantees to converge if all states continue to be selected. So if your random choice of selecting states is random, you have guarantees to converge. But that's kind of just an asymptotic result, right? Like if you have billions of states, in practice, in theory, I will converge. What happens in practice is, again, the computation. So one of the big questions, and we'll come back to this point again and again, is that can you select states to back up intelligently? So for example, maybe the agent experience can act as a guide, right? So whenever the agent kind of navigates in the environment and takes actions, maybe those are, or maybe the more frequently visited states should be updated more frequently, right? So there are three simple ideas for synchronous dynamic programming. There's something that's called in-place dynamic programming. There's something called prioritized sweeping. And later on, we're going to see in the context of deep networks, there's something called prioritized what's it called, replay memory. So this will kind of, you're choosing what to update based on the Bellman error. So for states where you're making big mistakes, you want to visit them more. For states where you're not making a lot of mistakes, you don't want to visit that more. Right now, you trade-off one versus another is something that, there's hyperparameters and stuff like that involved. And there's real-time dynamic programming. So let's quickly look at a couple of simple ones. There's something called in-place dynamic programming. This is a very simple idea. So if you're looking at the synchronous value iteration, you basically have to store two copies of the value function, the old and the new, right? Given the old, you update it to the new, and then they update. In-place value iteration only stores one copy of the value function, so it's kind of like in an asynchronous way. Given this value, you just update itself, right? Now, you have to make sure that your process doesn't hit the same state twice if you're doing it in parallel. That's what most of the time, and there are kind of mechanisms for doing that, locking and stuff like that. But this is just a very simple trick, and in practice, people tend to do that, hopefully hoping that you're not going to hit two states, like two processes are not going to hit the same state at exactly the same time for the update. This is prioritized sweeping, which is to say use magnitude of the Bellman error to guide the state selection, right? So you can say, find me a setting, find me states where this is the maximum, right? Now, obviously, if you have billions of states, how do you do that? Right? You don't want to go through all the billions of states and say, well, this state is the maximum, so now I'm going to update it, and I'm going to spend the next 24 hours figuring out where I'm making errors. So generally, people sort of maintain some queue of, oh, I'm seeing this state, I'm seeing a huge error, so I'm going to put it in the queue. And then the next time you see on some states you don't see big error, maybe you don't put it in the queue. So there are some more like traditional computer science-y type of algorithms to come up with the right way of trying to maintain a queue of the states where your errors are the biggest. Now, there are some tricks that you have to use. You always have to have some randomness in choosing arbitrary states. Because otherwise, if there are certain states that you never visit, you can't prove that you will converge, right? Because I can come up with an adversarial setting that for some state, I can give you a very big Bellman error. So you have to make sure that there is some probability of always choosing a new state. So it can be implemented efficiently by maintaining a priority queue. I also have to know reverse dynamics. So going from state to S prime, you have to know how to go from S prime to S. Real-time dynamic programming, this is sort of, you're basically updating the states that are relevant to the agent. So in this case, after each time step, you have a state, you take an action, you get the reward, you just basically update the state. Right? So it's kind of an online, you can think of it as an online learning algorithm, right? You're given the state, takes an action, you get the reward, you just update it. And then you randomly pick another state, you get the reward, and you just update that. Yes?
Transitions stationary?
Yes, transitions here are always going to be stationary. If the transitions are not stationary, like if this function changes over time, then all kinds of problems arise. Right? Because that means that your distribution is going to be shifting. Like whatever the optimal policy pi right now is also going to be time dependent, depending on how the environment changes. So in this class, we're not going to study that particular problem because it's on its own a pretty big research area. So couple of, in subsequent lectures, we're going to consider, sample backups. So for example, using sample rewards and sample transitions. So for example, one thing we can do is we can say, hey, how about if I'm in a particular state, I take an action, I get the reward, and I get the next state. And I'm just going to consider that as my sort of training example. Right? Can I train on that? And a lot of popular algorithms are basically using these sample backups to just do training, as opposed to running this long sequence. Instead of having the reward functional transition dynamics, instead of knowing what the transition dynamics is, because the environment gives you S prime. Right? In any natural environment, given just, you are in this environment, this is what I observe, I tell my agent turn left, The agent turns left, you get some reward, maybe 0, and this is what the environment gives you. You don't really know about what the transition dynamics is, but you have a sample from the environment, right? So maybe you can start training these models based on samples, which is what a lot of algorithms are doing, because it's very difficult to construct the dynamics of the world. Sometimes it's called model-free, because there's no model of dynamics, right? No advanced knowledge of MDP required. So the environment gives you the reward, and the environment gives you the next state, breaks the curse dimensionality through sampling. So if you have unbiased sampling from the environment, then you don't have the cursive dimensionality problem, and cost of backup is constant. So it's independent of the number of states. This is where the Monte Carlo type of algorithms come into place, right? And we'll look at some of those in the next class. These are sometimes called model-free methods, because again, they don't require the dynamics on the environment. So it has advantages and disadvantages. The advantages is that sometimes when you work with a real-world setting, because you can bypass the dynamics, you can actually learn interesting models. They also have disadvantages, because maybe if you can build the environment of the world, if you know exactly how dynamics is changing over time, that gives you a lot of information, right? It tells you something about you can simulate the whole world forward. So there are two camps in the community. Certain people believe in model-free because they basically say there's no way we can model the real dynamics as long as we get samples from the environment. And there are people who are basically saying this is just completely crazy, like this thing here. You should first build what the model looks like, right? And then figure out how to do, what the best set of actions are. Because you always know something about the environment. The environment is not like a random set of states floating around, right? So and in many cases you might know, like if you're building a robot, you might know precisely the dynamics of the robot, right? Like if you tell the robot move 5 centimeters forward, the robot will move 5 centimeters forward, right? And you can model that state with some noise around it. But maybe in many cases you know what the thing is. So if you can take that into account, it's almost like having a prior knowledge. And then there are people in deep reinforcement learning community, like more from machine learning background, that basically say, forget about models. We're going to learn everything from data in an end-to-end way. Right? We're going to learn the whole thing. Right? And then there are people who basically say, that's too crazy. Like you actually have to build a model of the world to be able to do something useful. So you kind of like see papers on both camps. It has an appeal. This has an appeal that given just samples, you can learn the whole thing. Right? So from a machine learning perspective, it's exciting because maybe you can learn things that the realistic model you will never be able to build the model that can do it, right? But in many cases, sometimes it's hard to analyze what these models are doing. So we're going to look at both in this class. There is also a class of approximate dynamic programming values, and this is actually a precursor to deep reinforcement learning. I think we in deep reinforcement learning community, we kind of like stole these ideas in the 90s and kind of renamed them. But these ideas existed a long time ago. So what you're going to do is you're going to use a function approximation. Right? Think of V tilde here as a neural network. Given the state, you pass it through a neural network parameterized by some parameters W, and you get the number. Okay? And you're going to be applying dynamic programming to V. So this is sometimes called fitted value iteration. For each iteration k, you sample the state. And for each state, you estimate the target value using Bellman equation, this sort. And then you train the next value function. So you're basically saying, I want this to be equal to this. So, if I can just subtract, set it to 0, that's my objective function. That's effectively what deep Q networks are doing. So if you look at a lot of interesting work recently in the last few years, deep Q networks and all kinds of deep reinforcement learning, they sort of came from optimizing this setting. And later on in the class, again, we're going to look at this, but the key idea is you do this parameterization. You're building parametric function that approximates the value function, right? So think of this as if your state is an image. A V could be a convolutional neural network. that just goes, takes this large image, and produces a single value. Is this a good state or bad state? Right? And it turns out that by optimizing this thing here, you can actually optimize and backpropagate through these parameters. That's exactly where deep learning is useful. So you can backprop through the value iteration and such, so that you can learn this parameterization. Okay, so next class, we're going to start looking at model-free reinforcement learning. We're going to start looking at Monte Carlo and temporal difference learning. And hopefully, the first assignment is going to be out on Monday, next Monday.